Here we are with integration by partial fractions, where the denominator has a quadratic and a linear term. This is my third time starting up this video, so cross your fingers and hope I make it through. What we're going to do is play the game where we say, well, this integral is a great big mess. I don't want to deal with it. But look, it does have a product in the denominator. Maybe we can blow the integrand apart and return it to its original form where the denominators were in separate terms, and then maybe it's easier to integrate the other version of the integrand. So what we do is we take a look at the original denominator and we say, well, we can't factor the x squared plus 4 anymore, and 3 minus x is just a linear term. And so if we were to break this apart into possible original contributing denominators, well, they'd be x squared plus 4 and 3 minus x, and nothing worse than that. And then we say, well, we're going to assume that these fractions are as simple as they are going to get, because if they're not, well, then we would simplify them further. And so on top of a quadratic would be at worst a linear function, and on top of a linear function would be at worst a constant. We just have to discover what these constants a, b, and c have to be to make this equation work out. And then we can trade the mess on the left for the messier but slightly easier version on the right. There's a couple of strategies here. We are going to go with the strategy by which we cross-multiply with the original denominator to clear out every fraction. When we multiply the left side by its own denominator, we leave behind its numerator. When we multiply this term by the big denominator on the left, the x squared plus 4's cancel. And we're left with that. Let's make this b a little bit better. There we go. Ugh. Okay. That's ugly, but I'm not going to start this video a fourth time. And then the term on the right, when we multiply it by this big denominator, the 3 minus x's cancel. And it's not pretty, but at least it's not fractions anymore. So there's two strategies here. One is we either multiply out this whole right-hand side, and there's going to be some x squared terms, and there's going to be some x terms, and there's going to be constants. And then we could take the coefficient of, say, all the x's on this side and say, well, that net coefficient has to be 3. And that would give us one equation with a, b, and c in it. Or c wouldn't actually be in it, but a and b would be in it. We would do that for the x squared, and for the constant, we'd get 3 equations and 3 unknowns. That's one strategy. It's usually not pleasant. The other strategy is to say, well, you know, this integral works for all values of x. This algebraic expression has to be true for all values of x. Well, maybe not x equals 3, but because that's where it's not defined. But we're all friends here, and now that we've cleared out the fractions, well, you know, we could plug in x equals 3 into here if we wanted to, even though this technically is defined at x equals 3, but this isn't. We're gonna ignore that legality, and we're going to say this thing has to work for any possible value of x, so let's pick some clever values of x that will help us discover our constants. For example, if I were to say, hey equation, what do you look like when x is equal to 3? Well, this left-hand side is 3 times 3 plus 4, 13. Well, when x is 3, that is 0, so this whole term is gone. And when x is 3, well, we have 9 plus 4 again. And we end up with this. That tells us that c has to be 1. Well, let's pick another value of x. X equals 3 was really the only immediately obvious good value because it makes an entire term drop out. There are no values of x that will make entire terms drop out, but you know, x equals 0 is usually a pretty easy value to work with. And when x is 0, this left-hand side is 4. This right-hand side starts with 0 plus b times, when x is 0, that's a 3. And then over here, well, when x is 0, this is a 4, but c we now know to be 1. And so we can finish off that side like so. And then this is 4 equals 3b plus 4. The 4's cancel. 3b is 0. So we've now discovered that b has to be 0. And we need one more value of x. Well, we've already used 0 and 3. We can pick 117 if we want to, but that would be ridiculous. How about 1? When x is 1, that looks like a 7. When x is 1, this is a plus b, but we know that b is 0. And when x is 1, that looks like a 2. And then over here, well, again, we know that c is 1. And when x is 1, this is 5. So here's an equation that happens to have a in it. There's a 7 and a 5. Yeah, so how about 2 equals 2a? That wasn't so bad. And so now we know that a is 1. And so the original integral, I'm not writing it, but I'm going to say the antiderivative of this is the same thing as the antiderivative of this with the values that we've discovered. We've discovered that a is 1 and b is 0. So that term is 1 over x squared plus 4. Oops, sorry, x over x squared plus 4. 1 times x plus 0. I'm sorry, you have a left-handed instructor here. And then for this one, c is 1. And now we've got it here. Now at this point, you wipe the sweat off your brow and you say, oh man, I can do this. This one's going to be a u substitution, right? X squared plus 4 is u. X would be 1/2 du, etc., etc. And this is also a very tidy substitution if you even need to do that. But ultimately, this is going to be a natural log. This is going to be a natural log. So I'm going to leave you with some fun. The partial fractions part of this is over. The conversion of the nasty rational function, blow it up into its individual pieces, resolve the constants, and do the new and improved version of the integral that has more pieces to it, but each individual piece should be easier than what you started with, and carry on from there.